at least in theory, it should work.
If you changed anything else about that, though, if you had like another lambda, do you have to do the assembly again?
Yes.
And then
Yes.
right.
That's why you probably will create a new task, which would be like assembly and run.
But it's just exactly.
But the thing is, when you develop stuff for Spark, you don't most of the time use that. You don't connect to cluster. You just have the local mode enabled, and you run your tests on local mode, and you just don't care. When you have the integration tests, because you still have we have that serialization problems. Those will not happen here, because if we run that on a cluster mode, as you guys saw in the beginning, we were having those lambdas and it worked just fine, right? Only because the cluster was emulated. It ran on the same JVM, so it had that class path ready with it, which was just working all together.
So in real life, if you're running on a cluster, you have to have the agile?
Yeah, pretty much. There's also, there are different ways, so I don't have that much time to cover that, but there are different ways to actually trigger the execution on a Spark. There are even scripts that which are called like Spark submit or something, where you provide your application. So a different way to do it. But if we are doing this the way that we are doing right now over here, you probably most of the time have to provide that add jar for it to work. Okay, so how are we on time? Not that good. All right, so let's refresh our Spark guide. Hey, now we have some information, right? We have now some application that we're running in our system. That, remember that set name that we had? It's over here, so we know which application is it. And now let's see the details. But wait, we cannot see the details. So if your job is running, right? It's going to be here, running application. It's going to be wrong application. You can click it, and you get a lot of details about that running job happening in real time. But after it's finished, then all that is dropped, and you cannot get any details. However, what you can do is you can provide to the configuration something which would like set Spark. I remember name. Log enable, and the value is true. So I think that's the. I will just check in a second. So what it will do is, while it will be evaluating your program, it will be just pushing the events to some storage mechanism, on which you can later on the system can read those events and give you all the details that happened in the system.
Event log.
Oh yeah,
enabled.
event log. Thank you. Event log. Yeah, I knew something was not right like this one. Yes. So let's try to run it one more time. Okay, while it's running, we also have to instantiate. So we're gonna go one more time to our Spark installation folder, and in the sbin folder, there's start history server. So that fires up yet another web application that will read those events and provide all the information that you need. And it will read from a folder. If you don't have that folder, it will tell you the path to that folder is configurable. But you can stick with the default one. It will be just the easiest way to have it running. So now if I refresh that, let's see. And yay, now I have some information about what was going on in my system. So what I have here is, how much it took, how many stages were there, and how many stages succeeded, how many jobs it need to fire up to actually run. There's a visualization of time, but more important stuff is actually if we go to that job. So first, the thing that we get is a better representation of state.
I'm sorry, how did you get to that? I'm on the console, and I started the history server.
You started, so now click on, do you have any job that run? You don't have any job, right?
Oh, right, yeah.
You would have to run. You wanna do the steps? Okay, so.
No, I don't want to take the time,
Just quickly, like whatever. So if you, for example, take that serialization issues program, add this line to it. I'll just copy paste that. So it's gonna be here. Spark event log enabled true.
Oh, so if I don't have that, nothing's going to show up on the.
Yes, because it will not be saving events.
I have other stuff that's broken, so.
Yeah. Okay. So if that one, it will have the history server has all the information. Now, what you have is for that job, you have a better visualization than to debug string for your stages, so you can actually see what's going on, right? Like so, the first stage, the second stage, and stuff like that. You have more detailed information over here, so how much time it took, how many tasks it executed, what was the shuffle read, what was the shuffle write. We'll talk about it in a second, what those are. And we can go to a single stage as well, and you get a bunch of other information as well. So this is, we are getting right now to the more complex stuff, the stuff that you're going to need if you run in production. So you know, like the statistics, like on average, how much time it took to calculate it, how much time memory it needed, what was the garbage collection time for it to actually be executed. You can have that DAG visualization here as well to know exactly what was going on. There's also cool visualization of an average, how the task for a given stage was performing. So the green part is your logic running. So it's the thing that you have. The first thing you need to have is have to have that scheduler create all the things, the physical plan and stuff like that. It takes time. Then there's time, how much time you deserialize your task on executor. If you're gonna do shuffling, there's also time to do some shuffle writes. So, on general, if for example your green part is really small, while the red and then the yellow are big, you know you're doing something wrong because your single task might takes 10 seconds, but out of 10 seconds, I don't know, like 5 are deserialization, 3 are shuffle write, and only like 1 second will be your actual business logic. So you know something is not right. Now, how to fix that? We will go into that in a second. I just wanted you guys to know how to use that Spark UI to understand what's going on. All right, so they wanted to add something here. Yeah, there's some additional matrices that you can see, like.
And in production, you normally have that history thing enabled in your code?
Yes. Yes, and also there's since version 1.5, I think, there's also the REST API, so you can get that information programmatically. Because what we had to do back in the day was actually just read that HTML, pass it, and because you want to have the monitors, like you want to have your system screaming like this is not doing the thing it's supposed to be doing, and for the only way to do it was just reading that stuff, and that was crazy. Yeah. So just a quick overview. So what we understand just one thing here is that just a clarification. That worker over here, as you guys see it, has 15 gigabytes of memory available. There's a JVM process running on a worker that represents that worker, so we can take jobs and calculate it. But it will be not using that memory. It actually has very small footprint of memory. Because when your calculation comes in, it's like the master is sending him like, this is just to calculate that task. What worker will do is it will trigger a new JVM on which your task is going to be evaluated. So your tasks come into the worker instantiates new JVM, runs your task, sends back the results, and kills the JVM. Why is that? Because this way you can actually configure the stuff that you're doing. There are configuration flags. Like for example, you might be saying, listen, you'll be calculating this thingy, but use only 1 gigabyte of memory. So your worker might have 15 gigabytes, but you're specifically saying, for this task, just use 1 gigabyte, right? So just for you guys to have that notion that for each of the tasks being calculated on the worker, there's going to be instantiated a new JVM process with all the configurations that you provide. Like for example, add jar would be one of those, right? Instantiates new JVM, adds that jar you added to the class path, calculate that thing, and kills it. Okay? So when the new process comes in with a different class also named user in the same package, there will be no conflict because it will just create a new JVM with the new configuration.
That makes sense.
And it's shipping that jar out to each time for each.
Yes. Yes, but if you send petabytes of data over the network, sending a few kilobytes of data isn't that really much of a problem.
Well, I was just asking, like, it's like every single time?
It's broadcasting. It's using a protocol which is close to torrent.
Yeah.
Cool.
Yeah, and those configurations can be found. I will of course share those slides, so whatever link I'm posting there, those will be available. Okay, so now the question is, why GroupBy has a major flaw? As you remember, how much time do you have? We'll manage more than an hour. As you remember, what GroupBy does is basically create new partition sets. So you have some partitions, and after GroupBy you will have a completely new set of partitions, right? And it will create a partition for every key, right? If I have a key A, all the values of key A will be on the single partition. B is so on and so on. And this is really cool if your data is sort of evenly distributed, right? So for A, you're gonna take like, let's say 1 gigabyte of data, 1 gigabyte and a half, I don't know, 600 megabytes. But what if your data is like 1 giga for like for A 1 gigabyte, for B 1 gigabyte, and for C 30, right? This is creepy because what it will do, it will try to create a partition, put all those values with key C into single partition, 30 gigabytes of data, and will send that to the worker. But the worker has only 50 gigabytes of data available. I mean, how much of it available? As much as you gave it in the configuration file. But let's say you gave him like the maximum, 15 gigabytes. It will not fit, right? It will explode with out of memory exception. It will not survive. It will just, die. No fault tolerance here. This is really, really not funny thing if you run it in the first time, because everything worked with tests, everything worked with staging environment. QA engineers were just happy. You run the whole thing on production and explodes. Because, just a reminder, the partition will not fit in the memory of the executor. All right? So now the question is, what can we do about it? What can be done? And the answer was ReduceByKey, but instead of giving you the answer, what are we going to do? We're going to do something really funny, and we're going to look on the Spark code base. Funny? Sad?
Haven't seen it yet.
What you gotta do?
Okay, so we are looking at, so this is, we are not looking at the RDD Scala, because as you guys remember, those methods like GroupBy and stuff like that, they only live for RDDs which have a key and a value, so those are implemented in a separate file. So they are only available for you if your RDD is of a type key and value. But all the methods are here. And there's one particular method I want to explain you, and once we know that how that method works, we're going to understand everything else. All right? So the method is actually, so the thing is, it's actually now that method, but it was added just recently, so it completely screwed my idea of how to show you guys the example, but we will survive, no worries. So, just give me a sec. Okay, so the method is called CombinedByKey. Okay? CombinedByKey takes a lot of parameters, but we are only interested in those three. And we'll try to think of how we could actually implement GroupBy, word count, without using GroupBy, and sort of it will survive the scenario where data is not evenly distributed. Okay? So let's imagine that we had that data set in all Shakespeare that, let's say, Shakespeare is always using, oh my God, right? And it's not evenly distributed, and suddenly it explodes for God. So, and we want to survive this scenario. So instead of using GroupBy, we're going to use, let's say we're going to use, for a second, we're going to use CombinedByKey. So CombinedByKey takes 3 parameters, more, but only the first 3 are the important one here. First one, and all of them are just functions. So the first one is called createCombiner. So what will happen is that, we had those partitions with all those different keys, like so in this partition ABC, ABC, and ABC. It will Spark on each of the nodes locally will run the same program. So each of the nodes will run the same thing. So what they will do is for each of the partition, they're going to go line by line and look at the keys. So he takes the first line and sees a key he haven't seen before. The first line. Let's say it's a key A. All right. So I haven't seen that key before. So for it, I will call the method createCombiner. I don't know if I have a. Okay. So you know what? I think I have a. So instead of showing you guys the code, yeah, I have. Do I? Will be just simpler. Okay, so well, we're not going to use ReduceByKey. What we're going to use is we're going to be using CombinedByKey. So CombinedByKey. Okay. So the first function, and it doesn't have to compile because I just want to go with the rest of the examples, but just quickly. So what we want to do right now is that if you found that value, that key for the very first time, whatever that was, that key, that you will get that the whole value here, just return 1. Okay, so just back to that example, it was running out in each of the partitions locally on each of the nodes, found the key for the first time, fire up that function, the first function, which will return 1. Now, it will continue. So let's say it goes to the second line. There's a key with value which is B. So it call the first function one more time. So for B, it also will return 1. But the third line here is one more time again A. Okay. So now it will call the second method, merge value. So what that method will do is it will have our previous value, so our 1 for our A, it's going to be here accumulator. It's going to have our value, and what we are saying, well, add to accumulator, just add 1. Okay? So, but the difference is right now, just this thing is happening locally on each of the nodes. There's still no data flying around. There's no problem that we have not evenly distributed amount of words, right? Because it's still running locally on each of the nodes. So with those two methods, we're gonna get partial results. So we're gonna get like for A, we had seen 3 A's. For A, we've seen 17 A's, right? And so on and so on. So what we still have to shuffle, right? We have partial results on each of our partition, we want to have the final result. We want to know how many A's were, globally. So that thing still has to fly around the cluster, but we will be not pushing everything. We'll be pushing partial results, just an A and the result, not all lines starting with A or words starting with A. Is that clear? So once that we had those partial results created with those very first two methods, those will shuffle, those will travel throughout the cluster, and now we just have to combine them, right?
Is that supposed to be like a parentheses, ACC, comma V for the function you're passing?
Yes. As I said, it's not going to compile. I try to.
I just want to make sure I understand. So it would be a function of two arguments.
Yes.
Yeah.
Yes.
Okay.
Sorry for that.
Confused me too.
So okay.
Interesting.
And so the last one will be just summing those two values together. It requires shuffling, right? In order for the last function to work, right? We have to push those partial results through cluster, but the thing is, those are going to be really, really small. And well, you still might end up in a situation where this will explode your memory, but it's really, really rare. And then you just have to probably just extend your memory.
Shouldn't be the number of entries in the next stage partition should be equal to the number of partitions in the previous stage.
Number of
Did that make
partitions.
sense?
Number of partitions in the next stage is going to be corresponding to number of keys.
Well, but if each partition has a whole bunch of different key counts,
Yes.
when you shuffle those,
Yes.
for each key, that partition that is all of one key,
Yes.
the most it's going to get is one of those keys from each of the previous partitions. So if you have 8 partitions here, you'll only have a maximum of 8 messages in that partition for that key.
Yes, pretty much. That's why there's no lot of traffic going on
Right.
internal. So now you guys remember how we actually, and I can show you
That's a
somewhere
drastic
here.
so you're just shuffling, so you're shuffling.
Maybe not.
Just one minute. Beautiful.
Okay. What the? Okay, so we had that implementation that was using ReduceByKey, right? We didn't use actually CombinedByKey. We used ReduceByKey. But if we look for the implementation of ReduceByKey, do you see what it's using internally? CombinedByKey. So what's the difference? Because CombinedByKey is very generic. It can take the elements of one type and create you the elements of a different type. In ReduceByKeys, we had integers and we were returning an integer. So that's why you had that, you could only just provide one function. But there's also aggregate by key and stuff like that, and all the I'll build just based on that method. All right? Cool.
Summary, don't use GroupBy.
We're not going to do that midterm exam because that was supposed to be an hour ago.
Yeah, we all get A's.
I was just thinking it's going to be university, it's going to be fun. But I never had a chance to be a professor. But anyway, all right, so we've been here, right? What's the RDD? It's not the first slide of this presentation, even I know it looks like one, that one, because we talked that RDD is a resilient distributed data set, and we had basically that notion of it, right? We had some file or whatever data, and it was available of each of our nodes, right? This is this notion, this abstraction that we have for an RDD. I hope so far, after 3 hours, that you guys had that notion of what RDD is. My question would be how that actually is implemented. And we're gonna see just that. And it's not really because I want to brag, I know how RDD is implemented. It's because that knowledge is essential to understand stuff that are happening, especially if you have production errors. This is, and if you get that, then any question that you will have for Apache Spark, before you Google it, and you've probably read burrito blogs on the Monad, you know that all blogs have the truth. They might be crappy blogs. So before you do, it's always wise to actually look at the Spark code base. And with stuff that I'm going to show you in a second, it's just going to be easy. So in order for RDD to be computed, it needs 3 information. So as you remember, RDD is a trait, right? An interface for Java developers, and different implementations of that trait. So if you want to construct a new RDD that will work in Spark, that would be a cool exercise. We need 3 informations. So the first one is the pointer to a parent, right? Because we create a new RDD, flat map, filter map. So if we run count on the last one, for him to be computed, he needs to know the history, of his how you call it, parents, lineage history, something like that. Also needs to know how to partition its data internally, and needs to know actually how to evaluate itself essentially on each of those partitions. So let's look at the partition part, because we covered that, it should be easy. So partition, it represents a subset of data within your distributed collection that you already know. Now the question would be how that, and this is the method that you're going to have on an RDD, the get partitions, and it returns an array of partitions. And the question would be how that method is implemented. As it turns out, the implementation varies, and it depends on the type of RDD that you are working with. So let's, for example, take the Hadoop RDD. So this is the RDD that you're going to have return when you're going to call the text file method. Okay? So how Hadoop RDD is partitioned in exactly the same way how it is chunked and splitted in the HDFS system. So this is HDFS, this is your file, which is already split it into small chunks. So how it works in the HDFS, you have a few nodes. So that first chunk might live in this node and that node. The second one might be living in the first and one as well. The third one lives in the first and the third, and so on. So if one of those nodes dies, we can still recreate the whole file. So HDFS already provides this abstraction of dividing big file into smaller chunks. So we can reuse that information, right? If the Hadoop RDD needs to implement this get partitions method, it will just use it. I know it looks scary, and it is, but there are only 2 important parts. The first part is get splits. So it takes those HDFS splits and returns it as an array here and includes splits. And what are we going to do? And yes, it's imperative code. I know it's a functional programming conference, but Spark, deal with it. So it's just taking an array, new array of partitions. Its size gonna be exactly the same as the size of splits in the HDFS system, and it just basically goes in a for loop, split by split, and creates a new instance of partition for that split. That's pretty much it. Here we have that Hadoop RDD journal, and we call filter on it. So the method here from March is RDD of a type map partitions RDD. The question might be how that is partitioned. So as it turns out, map partitions RDD inherits partition information from its parent, right? There's no point to create new partitions. It's going to be this pipeline, right? You just have to take, whatever my parent had partitions, I will just, inherit that from him. So this is the implementation. That's all. That's it. Take the first parent and just, call partitions on it. All the implementation. All right. So pointer to a parent. So this is our example. We have some text file. We're gonna group by. So it's just I was supposed to have an image here. Just imagine this holds some kind of events. We are extracting date from those events and grouping by. So the date is gonna be a key. So we're gonna have a date and all the events that happened during that date. There's we're gonna then map over that pair. So for each of the date, we know how many events happened, and then we're gonna say that we're only interested in events that happened starting from March 2015. So this is how our code looks like. But Spark doesn't really know anything about stuff that you put in those methods. For him, this is just lambdas. It has to serialize, has no knowledge what you're doing. This is how he sees your program. That's it. All right. So this is the Hadoop RDD, which is partition, as you guys know. Where this is shuffle RDD, map first RDD, map, and that's it. And this is our notion as we had so far, right? Each of the RDDs has to point to its parent, right? It's not that simple. The way that it's that history is kept, there are two types of parent dependencies. The first one would be called wider dependency. So what we are saying is not only I have to know who my parent is, but also I'll have to grab data from more of its partition. I will have to what? Shuffle, right? And the other type of dependency is called narrow dependency. When you have a narrow dependency, then you know that you can pipeline your calculation. So when Spark is going to look at your RDD, whatever RDD you create, if you're going to see that you point to your parent and it's a narrow dependency, and he will know he can, keep on doing the same stage. There's not going to be any shuffling happening. It's going to be just pipeline, right? Until he reached narrow dependency, then he knows that the shuffling is needed. One important thing. So far, when we look at shuffling, you guys remember those arrows were actually the other way around, right? We were pushing stuff from that RDD to a second one, right? Why those arrows are like this? Because what I'm showing you guys right now is actually implementation detail. Just try to imagine how would you do a shuffling if you were implementing Spark. For example, for GroupBy. You want to push all those values with the same key to each of the partition. How would you do that? So what Spark is actually doing is for each of, yet again, since version 1.4, there are different algorithms that you can use. And there's a default one, there's another one that you can also change, but let's talk about the default one. So the default one works this way. It will first locally split into the buckets, like a local representation of partitions you're going to have for each of the partition. So each of the partition will like split that data locally, right? It's going to be kept in memory. If it doesn't fit the memory, it will start splitting stuff into the disk, into I/O. It's better than Hadoop because Hadoop was always splitting the disk, whatever you were doing. Here it will try to keep it in memory. If the memory is full, then it will try to put that and serialize it into disk. So it's gonna put for each of the partition those little buckets. Once that is done, then the second partition, the next entity, he's observing the situation. He's gonna be notified. Oh, he's done. So now I can actually take. So from that partition, I'm gonna take this from that bucket, and from that partition from that bucket. So all the A is gonna go here, and the second one is gonna be okay. So I'm gonna take B's and B's and B's, right? So and why this is important to? It's actually important even if you evaluate your Spark code. You're gonna see shuffle read and shuffle write, those two concepts. So the shuffle write is gonna be how much data was actually put into those little local buckets before it was sent over the network. And shuffle read is actually how much data was read from those buckets, and those may vary. It's not always like gonna read everything because not always need everything. But this is implementation data, but just so you guys know what we are talking about. So this is how internally it works. And so then we have tasks. So we covered that stages and stuff like that. All right. So any questions for it? Or if you have questions, then maybe at the end of the session, all right? So we can finish the whole thing in 50 minutes. All right. So the last one thing was how to evaluate the internal data, right? You guys remember this was just here still Doug, right? It's basically a recipe, a plan of how the thing should be evaluated. We call an action on it, like collect, and it triggers the execution. My question is how the collect method is implemented. So, as it turns out, there's only one method implemented at Spark, and all other actions are just using that method. And the method is called run job. Okay? And all actions that we have on the RDs are implemented using that method. So if you understand this, you understand any other implementation of action. So it will take 3 parameters. The second one will have a default value. So the first parameter will be the RDD on which you want to evaluate something. The second one will have a list of indexes to partitions on which you are interested in. Most of the time you're interested in all partitions that are on the RDD. And the last thing would be a function that will be run on each of the partitions. Okay, so it takes the iterator of, so we have partitions of type T, right? And so we're gonna get is, for each of the partitions, you're gonna get iterators of that whatever's, and you're gonna have to provide a value. So this is evaluating those sub results results on each of the partition. And then you're gonna get the final result is gonna be just array of those results. So just to put that into context, let's see how collect is implemented. So what collect will do, if you run collect on RDD, it's gonna call this method run job. It's gonna provide itself as a reference, right? Me, let's calculate me. And that method is just saying, okay, you gave me just an iterator of stuff that you have on your partition. I'll just transform that into array. That's it. And we concatenate those sub results into a final result that we return. Is that clear?
Mm-hmm.
Pretty
Can you go back to the last slide? So you had 3. What exactly was the partitions?
So sometimes, so it's like sometimes you might execute a job where you provide RDD. That RDD has, let's say, 100 partitions, but for whatever reason, you want to execute it only on 5 partitions. Like you want to do sample, right, or something like that. You don't need everything. You just want to run it on a few partitions, and you'll be just fine, right? So that second parameter will just tell you whether you want to use all partitions or just subset of partitions. And here we're just saying, use everything.
So it's a number to run on each partition because it's a sequence division.
So, yeah. So it just gives you an index to like
Index.
yeah.
Okay, gotcha.
So count. How count can be implemented? So it's one again, give it itself, right? And for that method that takes the iterator, well, we are just saying, all right, for the iterator, give me the size of that iterator. But it's not, it's using some iterator, get iterator size util because of some magic happening internally. But basically it's iterator.size, and that's it. And so we not get the result of run job here will be just array of sub counts, and all you have to do at the very end is just sum it, right? That's pretty much it. Now the take, it's a bit complicated, and I'm just putting that not to confuse you, but to show you just one important thing. Because what I thought for a very long time was that for each action, I would get a single job. That was my notion of how the things work. And I sometimes was confused that sometimes I had like an action, but on the Spark UI, I saw more than one job. The take is one of those rare scenarios when you're going to run few more jobs than actions, actually. Because think for a second, take should give you like a sample of your data, right? Mm-hmm. But if you have that data in some order, if you just take the very first part, let's say I want to have 5 elements, right? If my implementation of take was simply take the first partition, take the 5 elements, return it, that would be very naive, right? Because that doesn't give me that data might be sorted or whatever, and I don't get like whole distribution of the data set. Would be better if I, for example, if I want to take 5 and I have 5 partitions, I could take the first element from first partition, second element from second partition, and so on. So my sample is like more closer to the real world. That's why that implementation here is recursive. It calls the run job a few times. Actually, it calls itself a few times, which internally calls run job a few times.
So isn't take on a Scala collection just?
On Scala collection, it's
it's ordered. It starts at the beginning.
Yes, but we are not talking about Scala collection. We are talking about RDD. So they implemented.
So the semantics really have changed
yes.
because you want to be distributed across the partitions. Okay.
Exactly. Okay. So having that and yet a few more minutes, we can now test what we learned. So now let's think. So we had that code I told you guys before. So this is a list of events that happened. We group them by date. So our date becomes our key. Then we map over it. So we have still the date is our key, but the number of the value is the number of events that happened that given date. And we gonna filter that. So we're only interested in events that happened after 1st of March of 2015. So this is our to-debug string, but you guys know that already, right? One stage in the second, right? This is obvious right now, hopefully. And we're gonna call the events count. We're gonna know how many of those are in our system. So this is the stage number 1, right? Right?
Yeah.
Okay, so this is our timeline. This is our cluster, 3 nodes and 5 partitions. So we run it. Those are being evaluated, right? Evaluated. Now what should happen? Come on, you know it. Shuffle, exactly. I was hoping for it. All right, so you guys know shuffle takes time. Takes a few more minutes. And when it's done, we're gonna trigger yet another stage. Awesome. So it's now just check it out. The number of partitions change, right? So we now have 4 partitions. So calculate the first one, the second one, the third one, and fourth one, and it's done. Now the question is, what should we do to refactor it? Any suggestions?
Make it 3 partitions on the filter in the second
Okay.
stage.
I could do it if that was in my Emacs, but because I have slides and only this one button, will go my way. So the first thing that we could remember that shuffling was really expensive, right? But we already know that filter is the data from last 10 years. And we are interested in only a year and a half worth of data. So if we just move that filter up front, right? The shuffling will be a lot smaller. Why? Because there will be a lot less data to push throughout the network. Right? That's one thing. The second thing, remember how I told you at the very beginning that, and there was a question for it, that the number of partitions correspond to the level of parallelism that you get from Spark? So this is exactly where it, shows its potential here, a problem. Check this out. We had 3 nodes, but 4 partitions. Those 3 were running in parallel, right? But now when those are executed, and we have the last partition to be executed, we're going to have 3 nodes which are not, one node will be executing the last partition, right? And 2 other will be just, waiting, whatever. We will no longer have the cluster. The cluster is going to be there. Actually, I have it just to show you. This is this, right? First is being evaluated, second is being evaluated, third is being evaluated, and now those are being, the fourth one is starting, right? It's still a little in parallel, but those guys are finished, and now we are running the last partition on a single node. So we are no longer have any parallelism here, which is a crappy thing to have. So what can we do about it?
Repartition?
Yes. So when you are doing any operations that gonna do a shuffling, so you're already creating that the data has to fly around the cluster. What you can do is you can provide a number of partitions that you're gonna have in your system. So you can say, not the default value, I'm interested in a 6. Why is that cool? Well, because this is gonna be an ideal scenario if every partition was executed at the exact same time, because it doesn't have to be like this, right? The data would be evenly distributed, but in ideal world, it would be just twice as fast. And the question might be, what is the why 6? Why not 2,000 or 1,000,000 partitions, right? So the idea is that the more you get is better, but at some point you're going to reach a moment where your partition is so small that the actual calculations on that data takes less time than pushing that stuff over the network, deserializing it, right? Serializing it one more time and pushing the results back to the master. So you don't want to have that situation. You want to have that at least like, that much time for data and that much time for other stuff, right? Something like this. The rule of thumb that they give you on a Spark documentation is that you should have at least, number of partitions should be at least number of cores in your cluster multiplied by number of nodes multiplied by 2. So that's like a rule of thumb. But what you don't want to go with that rule. What you want to do is you want to always monitor your things, because you might be in the situation where, for example, that doesn't work because this data is not evenly distributed. Maybe you need a little bit less. Maybe you need a little bit more. You always have to check like how your job is working on cluster.
It seems like you're going to be running more than one job on your cluster. So you're probably not going to have nodes sitting around not being utilized.
It depends.
But where this will make a big difference is in latency.
Of course. But I, for example, was working for a company. So it's a cool story. Can I have like 3 minutes for a cool story?
Yes.
So there was the first application I was writing for using Apache Spark. And it was a company that, so that company had customers, and those customers are the telecommunication companies, like T-Mobile, whatever, okay? So they were providing applications for those companies. One of the system that you have, like one of the programs, application that you have in the system is a billing system. A system that creates invoices. Apparently one of the most important one, because what's the point of running a telecommunication company if you're gonna charge it for it, right? So they had a solution running on Oracle, which was producing invoices for one of the clients. It took 50-something hours, 50, more than 2 days, okay? And it was already running on few very expensive Oracle nodes. And we were trying to find if there's a better way to actually do it. So my friend who was doing the proof of concept for this project, what he did, he took a part of that problem of the billing system, part of it, which on that legacy system was still taking like 20 hours, okay? And he re-implemented that using Spark, a different solution. He was doing proof of concept, so he was not only evaluating Spark, but he went from 20 hours to 20 minutes. But at 20 hours was calculating on an Oracle cluster, and at 20 minutes was on his laptop.
What?
So when the client saw it, it was like, and I'm telling this story is that because there are scenarios when you're going to use Spark with just standalone cluster. You're not going to use ER or messes. You're going to have your dedicated cluster only for you, because it's still going to be like a cluster somewhere probably in the cloud, because billing system is run every other month or every other week, right? So you instantiate a cluster, run it for like an hour or two, and just kill it. But you have your cluster for your own. So it's not always like that. But still, so this thing is still important. You still might have scenarios where your node's going to be just chilling, especially if you, for example, have mesos, and it will give you the resources, right? Mm-hmm. But it will not know that, for example, that resource is no longer needed, because maybe Spark needs it still, right? Spark knows it doesn't need it at the moment, but mesos that doesn't know it. All right, so the last thing you already know, CombinedByKey, right? We saw that. So we are eliminating the GroupBy. I'm not going to stay in that example because you guys already know it. Now, a few things about partitions. I said we can change number of partitions when you're doing shuffling, but there's also a situation when we want to change number of partitions, but you're not doing a shuffling. Like it?
I'm sorry, it seems like you blasted. The problem was just that last partition being, in the previous thing you were talking about, was the last partition running by itself.
Yes, at the very, so those three are end, right? Yeah. Let's say that this takes 10 seconds, right? So the whole thing takes 20 seconds right now, right? Because once those are executed, the last partition is being executed, but it runs on a single node, right? And those other two are just, not doing anything at this point. So the whole thing runs for 20 seconds. But if I make more partitions, then each of the partitions will be executed shorter because it's a smaller data set. But now those, the first one will run, second one, third one, but I have fourth one, fifth one, and sixth. So those, I'm almost all the time reusing. There's only like this small time over here, this little gap, when this last thing is being executed as a on a single node, right? This
So it's
only-
just about, so the solution was about the partition number, because then you went to combine by key, and I thought you were
Yes,
saying
no. So
played a role.
that was it. I was just
Yeah, okay, that-
okay.
all right, I see.
Sorry, I
Yeah.
skipped that. So that was it. We see that it's twice as fast, and then there was this last problem of, because we're still trying to refactor, we're trying to take that knowledge that we learned for the past 3 hours and to see if we can reason about our code. So, and we skip by the group by because the combined by key we already saw. Okay, so there's so the number of partitions we can change while we're doing shuffling, which is obvious. But there's also a situation like this one. For example, I'm reading some data, and when I extract it, and the number is too small. There's a method called repartition, which will change number of partitions, obviously, but it will trigger the shuffling, right? Because to change number of partitions, the data has to fly around the cluster, which is obvious, right? So you might wonder, what for, right? I mean, here it was already like a single stage, right? I just run it and it works. Now I'm doing repartition, and now I have stage 1, shuffling, and stage 2. That's true. But because of the problems that we discussed a second ago with that level of parallelism, if I had like 4 stages, 4 partitions here, and there's a lot of data, it's going to be worth for me to do the shuffling to make the data set smaller and to run that code. And there was Spark Summit 2 years ago. They were actually showing that in real life. So they had the data set, which was huge, like a cluster. Then the repartition, and they show it was just basically faster. You just have to believe that it's.
If you're repartitioning to a larger number, it shouldn't be that bad because most of the data will stay on the same node.
How come?
If one partition is assigned to one worker, if I go from 4 to 8, that you're just splitting the information into
Yeah,
2.
sure,
It stays
pretty
on the
much.
same node.
But it still has to fly around the cluster, right? But
Depends on implementation.
yeah.
Yeah.
But
I mean, that would be the efficient implementation.
Thank you.
Okay, I don't know. What we can do is
No,
actually we can look at the
slides.
Read the source.
Slides, I figured it out.
All right, so there's another method also called, so there's a scenario where we have right here. So we read a file and we filter, and we take only like from the last events that happened for last year, right? And this isn't really, and let's just imagine that we already have huge number of partitions here, like 1024. But why this is a problem? Well, this what we actually want to do is we want to make the number of partitions smaller. Why is that? It's because if you're going to run our monitor on our Spark, we will see we have a lot of those tasks. So if we filter most of the events from your data set, you will end up with partitions which are empty or almost empty. So the task will have to serialize that stuff, do almost nothing, or just discard because there's nothing in the partition, serialize the value 0, send over to cluster. So it's not efficient. So it's better to actually make the number of partitions smaller in those kind of scenario. And the method, which name I cannot pronounce, coalesce, is exactly done for it. So, and the cool thing is that if you make the number of partitions smaller, it will not shuffle.